So, as promised, I want to talk a little bit more about double replacement reactions. So these are the reactions where you have two ionic compounds that react and form two new ionic compounds. And because they behave in a very specific way, and because we see a lot of them, because they occur in water, this gets some extra time. So ionic compounds you sometimes hear called as salts as well. Sodium chloride, of course, is a very common salt, but there are many, many others. So, anyway. Ionic compounds, one of the reasons that they're sort of interesting is that, as I said, they behave in very specific ways in water. So the ions are attracted to one another because of their opposite charges, but they're not like physically connected by electrons as a covalent compound would be. So what happens when you dissolve them in water is that they dissolve, but they also dissociate. And what dissociation means is basically that they just come apart. They unstick, as it were. So you can write the dissociated ions just as individual ions. And that, if you were able to shrink down very small, like magic school bus style, and look in a beaker of water with sodium chloride and potassium nitrate, you wouldn't see sodium chloride and potassium nitrate. You would see sodium ion, chloride, potassium ion, and nitrate. So you would see them all independently floating around. And there are some videos and things that I'll have you look at that sort of illustrate that as well. If all of the ions in the reaction stayed aqueous, so they're aqueous here, aqueous. If they stayed aqueous, what would the products look like? They look exactly the same, right? Because your ions are just floating about independently. So, in order for a chemical change to occur with these sorts of double replacement reactions, one of the products can't be aqueous. Because if it stays aqueous, everything's just floating around. So one of the products has to become either a solid, a liquid, or a gas. A solid is going to be the most common one for us, but there is a particular situation that you saw in the lab and that we'll talk about more specifically that does result in a liquid gas situation. So if we look at an example, we have sodium chloride, silver nitrate, making sodium nitrate and silver chloride. So that's just our regular word equation. So that should look familiar to you. If we were to write that in symbols, it would look, again, this is just what we've done, sodium chloride plus silver nitrate, and this is our same AB, CD, making AD plus CB. So that pattern, it's just the same pattern that we've seen before. A couple of things I want to point out. Notice that both of the reactants are aqueous. In a double replacement reaction, that is going to be incredibly common. Nearly all the time, both reactants will be aqueous. And then, if you look at our products, Na-NO3 remains aqueous, but silver chloride is a solid. That is the species in this reaction that is what's called our precipitate. Because remember, it falls out of solution like rain falls from the sky. And we'll talk about how you know that soonish. So the way that we've been writing equations and the types of equations that we've been writing are called molecular equations, even though it's an ionic compound. The idea is that you're writing the ions or the molecules just together, basically. So this is just what we call the way that we've been doing it. It shows all the chemicals in a reaction, how they interact with one another. So it shows our pattern, AB plus B plus CD, very nicely. But for this particular type of reaction in particular, it doesn't show sort of what's actually going on at a microscopic level. So it's a good way to keep track of where the ions are going, but it doesn't necessarily give us as much information as we might want or need. So what we can do, and this is sort of the Miss Frizzle type equation that really shows how the ions are actually arranged in the water in which they're dissolved. So because they're ionic, because they're just held together by opposite attraction, as I said, they can come apart and go back together. And so this shows everything that was aqueous in our molecular equation is dissolved and dissociated in the water. So you show that by having the different ions separated, and they are ions at this point, so they do need charges. So ions have charges. So when you're writing ionic equations where the ions are dissociated because they're dissolved in water, you really need to make sure you include their charges. Okay, so undo the crisscross, write their charge. So in an equation like this, anything that is aqueous is going to be dissociated, because if you could, as I said, if you could magic school bus it, that's how they would look in the solution. You would have something like this. Oh, art skills. So, water. You would have little NAs and little CLs and little AGs. Oh my gosh, I'm sorry guys, this is not pretty. And NO3s. And what's going to happen is that over time, the AG and CL might bump into each other. And when they bump into each other, they fall to the bottom because they precipitate. And so that takes them out of aqueous solution. But the NO3 and the Na are still sort of floating around. So that's why we write it in this way. You might notice, if you are thinking sort of mathematically, that the Na and NO3 are identical on both sides of the equation. So if you're thinking mathematically, you might be thinking, if I have the same thing on both sides, do I really need it? So that brings us to the next type of, and that is what's called a net ionic equation. And a net equation is like a net profit or a net weight of a cereal. Looks at only sort of what's important. So then net weight of a cereal takes away all the packaging and it's just the cereal. The net profit takes away all the expenditures, the expenses, and it's just the profit. A net ionic equation takes away any of those ions that occur identically on both sides, basically the stuff that stays aqueous, and it focuses in just on the things that are actually changing in the reaction. So in this particular instance, Ag ion, silver ion, and chloride were the two ions that came together to form our solid. So those are the only two ions that are really reacting. And so we focus in on those and we just write the reaction that they do. The other ions are important because they're in our solution. We wouldn't have had the silver or the chloride without them, but they're not really participating in the reaction. And so they get their own special name. They are called spectator ions because just like spectators at a sporting event, they are there, they're important, but they're not actually participating in the sporting event or the reaction. So we have spectator ions, which stay aqueous the whole time, and then our actual ions that react form our net ionic equation. So it's a little math again. You get rid of what's identical on both sides of the equation. So this is a wordy slide, and for that I apologize. You need to have a way of knowing which elements, which species are going to be your precipitate versus what kinds of things are going to stay aqueous. And for that, of course, we have a set of rules, the solubility rules. So the solubility rules tell you of the items in your double replacement reaction that you predict to react when you do your, AD plus CB, what will they act like when they're actually in water? We can use our pattern to predict how they should combine, but we need some more information to know if they will really make a precipitate or not. And then just a reminder that the word soluble means that it will stay aqueous. It will stay dissolved and dissociated and stay the same in the products as it was in the reactants. Insoluble is not soluble, so that's the thing that becomes the solid or becomes the precipitate. Okay, so these are rules that you do not need to memorize. You'll get on your test a little piece of paper that will have all the solubility rules on it. They'll look just like this. They're also something, when it comes time to take the final, you'll be able to put on your note card. So you don't have to memorize them. There are some, I guess, that you will remember just by virtue of using them a lot. But what you do need to be able to do is recognize, what rule applies to what particular expected compound, basically. So, in general, you always start at the top and then go through them kind of in order. Rule 2 supersedes a lot of the lower rules. So if Rule 2 applies, then, you stop. So let's discuss. So the first rule is that most nitrate salts are soluble. The things with nitrate, which is NO3, of course, you know that. Most nitrate salts are soluble. So silver nitrate, for instance, is soluble. Next, we have most salts containing alkali metal ions, so that's group 1. So sodium, potassium, lithium, those are the common ones. Maybe rubidium, it's much less common. But sodium and potassium for sure, always soluble, that's our group 1A. And then ammonium is NH4 plus. So those are always soluble. So rule 1 and rule 2, they will stay aqueous. Rule 3, most chloride, bromide, and iodide salts are soluble, except when they contain lead, silver, and mercury. So we saw in our example, silver chloride was our solid, because that's an exception. Rule number 4, most sulfate salts are soluble, except when they're with barium, lead, mercury, and calcium. Okay. So those will be solids, they will precipitate, but any other sulfate salt will be soluble, it'll stay aqueous. Hydroxides, on the other hand, are generally insoluble, so they generally precipitate out. And this time the exceptions are the things that make them soluble. So anything in rule 2 will be soluble. Calcium, barium, and strontium hydroxides are also soluble, so they'll stay aqueous. Rule 6, most sulfide, so that's just S, not to be confused with sulfate, sulfide, S. Sulfide, carbonate, chromate, and phosphate compounds are insoluble unless they are with rule 2. So, for instance, if you had sodium chromate, that would dissolve, but if you put it with like silver nitrate, then it would become a solid. So your job will be to look at the predicted products based on our little pattern, AB plus CD yields AD plus CB. And you'll see of those two products, which, if any, should, according to the rules, become a solid. So here's another example. This one is nice because it shows what you do when you have a non-1 charge. So this shows it balanced. And then this again is just showing the ratios of ions that you would see if you could shrink down very small and look at what the container of water actually looked like. The net ionic, again, you get rid of the things that are identical on either side, completely identical. And those are what are called your spectator ions. This is a very special example because it is the one that we will talk about that behaves in sort of an unusual way. And it's one that you saw in your lab as well. So this is sodium bicarbonate reacting with hydrochloric acid. And you would predict that the products would be NaCl and H2 CO3. If you use the AB plus CD little scheme, that's what you would predict. But H2CO3 immediately undergoes a decomposition reaction. It immediately breaks apart to form H2O and CO2. So in your solubility lab, when you see bubbles, this is the reason, this is the reaction that's happening. So it's important to remember, if you see that H2CO3, it is going to break down into carbon dioxide and water. So you'll end up with 3 products, and 2 of them this time are not aqueous. We have a liquid and we have a gas. So when we write our complete ionic, I'm going to have our ions in the reactants. The reactants are always ions. And then in the products, only the Na and Cl remain aqueous. Water becomes liquid, CO2 becomes a gas. So the only things that are completely identical on both sides are the sodium and the chloride. Those are the spectators. The bicarbonate and the hydrogen come together to form the water and carbon dioxide. So both are included in the net ionic equation. Okay, here's just another example, again with non-1 charges, which is nice. Another example. This one's kind of yucky to balance. And our final example. This one is nice because it does show the balanced ionic equation, and it also shows that once you get to the net ionic equation, since all of the coefficients are 3s, you can go ahead and reduce that if you want to. So there you have it. What you do with double replacement reactions. All right, go finish your lab.